Well, hello students. We're going to continue now our lecture on the electron configuration of the elements and also on periodicity, or the periodic behavior of the elements. I broke these lectures up into two parts because I was a little worried that your attention span might be strained. I didn't know if you had the attention span of an excited electron in the 4s state. Oh, that's just one of those little chemistry jokes. Another chemistry joke. Sodium and potassium are walking to church one Sunday morning, and sodium says to potassium, "Oh, I had a rough night last night. I went out with the halogen twins." And potassium said, "Oh, tell me about it." Sodium said, "Oh, it was rough. I think I lost one of my electrons." And potassium said to sodium, "Are you sure?" And sodium said, "Yes, I'm positive." Okay, so in this lecture, we're going to talk about periodic trends of the elements, and we're going to talk about three important periodic trends, and those are the size, or the atomic radius of the elements, of the atoms of the elements, what is called ionization energy, and what is called electron affinity. The graph to the left shows the basic trends. The top one, the atomic radius trend, where the arrows always point towards increasing radius or size, in that case increasing ionization energy in the middle graph, and increasing electron affinity. Now let me point out this is the negative value of electron affinity, so in other words, increasing absolute magnitude of the electron affinity. Now we'll treat these one at a time, so don't worry if we're going quickly through this first slide. Atomic radius, the trend. Now, first of all, as you go down the periodic table, things get bigger, as you might expect. That's fairly obvious because the electrons are being placed into higher n values, which are further away from the center of the nucleus. But there is one counterintuitive trend if you look at the periodic table, or the outline of the periodic table, and that is as you go from left to right in the periodic table, that is, as you go from lithium to fluorine and then neon, as you go from sodium to argon, things, instead of getting bigger, they get smaller. Now, you might have expected that as you go from the left to the right, as you go from the lithium, sodium, potassium, group 1A, over to the halogens, fluorine, chlorine, bromine, and to the noble gases, that things would get larger because you're increasing the atomic number, the number of protons and neutrons in the nucleus, and you're increasing the number of electrons. However, actually the size gets smaller. The atoms shrink as you go from left to right. Now, why is that? It's counterintuitive, but it's because you're, in addition to adding more electrons into these orbitals, either in the s and p orbitals, you're also increasing the charge of the nucleus. And the nucleus has the effect of pulling down the orbitals, making them more and more compressed because of attraction between the positively charged nucleus and a negative charge of the electrons. So that's the one counterintuitive trend that we will see. And I will tell you in this class that there are only a couple of counterintuitive behaviors or trends that we run into in chemistry, and this is one of them. So it's just important to remember that as you go from left to right in a periodic table, things get smaller rather than bigger. And the next slide shows a graphical representation of that in the top. As you can see, if you look at the second or third or fourth row, any of these rows, that as you go from left to right, the elements get smaller. Of course, as you go down, they get bigger, but they get smaller as you go from left to right. The bottom part of the slide shows a more detailed graph of the atomic radius given in picometers, picometers. And it shows, as you increase the atomic number, it shows that as you sort of make a jump from one n value to the next, you will have a dramatic increase in the radius. But then as you go from left to right, it drops. It gets smaller and smaller and smaller until it gets to the end of that row, and it jumps back up again. So take a look at this and look at the graph above and just realize that this is one of those counterintuitive trends that as you go from left to right, things actually get smaller instead of bigger. The second property we want to talk about is what is called ionization energy. Ionization energy in some textbooks is also called ionization potential. So it could be either IE, ionization energy, or IP, ionization potential. Well, what in the world is an ionization energy? It is the energy needed to knock an electron away from an atom of an element. So if you look at the slide and the equation or the reaction sort of in the middle of the page, it's the energy needed for an element X, any element, and these are defined as in the gas phase, but an element X to lose an electron and become a cation. In this case, we have an X plus 1 cation in the gas phase. The energy needed to kick that electron out is called the ionization energy or the ionization potential. Now, what is the trend? The trend is that as you go up the periodic table, the ionization energy increases, and as you go from left to right, the ionization energy increases. Let me explain both of these trends. As you go up, you're dealing with smaller and smaller elements, and the electrons are closer to the nucleus, and because the electrons are closer to the nucleus and they're attracted to the nucleus, it takes more energy to knock them out or to remove them from that closer orbitals that are closer to the nucleus. Now, as you go from left to right, the ionization energy also increases. And if you think about this, remember we talked about how elements like fluorine and oxygen actually want to gain 1 or 2 electrons to fill their outer shell. So they don't want to lose electrons at all. They would rather gain electrons. Whereas over to the left side of the periodic table, group 1A or group 2A, ones with lithium, potassium and sodium, and magnesium and calcium, these elements have a single 1 or 2 electrons in these outer shells, which are out there, further away from the nucleus, and are easier to knock off. So it takes less energy to knock an electron out of sodium to form sodium plus 1. Remember, sodium had that rough night. But it takes much more energy to knock an electron away from fluorine to try to form a fluorine plus 1, which even saying that sounds fairly extreme. Now we can also talk about a first ionization, second ionization, third ionization, etc. energy for certain elements. And at the bottom of this slide shows an example of this, magnesium. For magnesium, we can talk about a first ionization energy, i.e. subscript 1, as the energy required to knock out or remove the first electron from magnesium to form magnesium plus 1 cation. And as you see, it takes about 738 kilojoules. That is, for these ionization energies, there will be tables in the book with numbers for the various values. But what is important here is to note that there can also be a second ionization energy, in which a second electron is knocked out of magnesium plus 1 to form magnesium plus 2. This IE2 value is 1,450. It's about twice the value for IE1. Okay, now follow this next argument. But to kick out a third electron to form magnesium plus 3 takes a much larger amount of energy. So essentially the key here is that to kick out 1 electron takes about 730 kilojoules. The second electron, about 1,450 kilojoules, but to kick out the third electron requires a much larger amount of energy. Now, why is that the case? Well, if you think of where magnesium is in the periodic table, it's in group 2A. It has 2 electrons in its outer shell, and it is, if you lose these 2 electrons from the outer S shell, the magnesium would revert to the electron configuration of the nearest noble gas. Okay, would have actually 10 electrons. It would be like neon. So it's relatively easy to knock out the first and second electron. But to knock out the third electron would mean sort of digging out one of those electrons in the electron configuration of the nearest noble gas, neon. That is, it does not want to lose one of those electrons because it has just satisfied the octet rule, and it doesn't want to give up one more electron. The point is that there are some trends, which I'll show you in the next slide, of the ionization energies, and these little trends with sometimes little irregularities in a pattern can be related to the electron configurations. Okay, so this plot shows the first ionization energy as a function of atomic number. And you should blow this up and look at it very carefully. There will be a plot of this sort in your book. These are irregularities in the plot of ionization energy versus atomic number. If you look at, if you go to the left and look at hydrogen to helium, of course it takes much more energy to knock out an electron from helium because helium has it has a filled outer shell. You go to lithium, it takes relatively little energy to knock that electron from the 2s1 orbital of lithium. It takes a little more energy to knock out the electron from beryllium, but then look what happens at boron. It actually drops, and it takes less energy to knock out an electron from boron than it does from the element to its immediate left, which is beryllium. Why? Because in boron, the electron in boron is it's by itself in a 2p1 orbital. So when it's by itself, it's easier to be picked off. We then go to carbon, to nitrogen, and then notice that there's a little drop when you go to oxygen. Why is there a drop? Well, going from boron to carbon to nitrogen, you're just adding an electron to each of the 2p orbitals, a single electron in each of these orbitals. And when you get to oxygen, you're pairing up 2 electrons in one of the 2p orbitals. And remember, there's a little bit of an energy expense to put 2 negatively charged electrons in this to occupy the same orbital. So it's relatively easier then to knock that paired electron out so that you then revert back to having 1 electron in each of the 2p orbitals. Okay, the point is that if you look at these irregularities and these little jagged patterns, they can be interpreted and tell us information about the electron configuration and what some of these subtle rules are. Okay, electron affinity. And again, I'll point out that the arrows that I'm pointing to are actually the magnitude, the absolute magnitude of the minus electron affinity. And that's because electron affinities tend to have negative values. Not always, but most of the time they have negative values, and what is key is the magnitude of this negative value. And we'll see later on that the negative refers to it being an exothermic reaction, which we haven't really introduced yet, but we will later on. Anyway, the trend, the pattern of the negative electron affinity, or the magnitude of the electron affinity, as you go up the periodic table, there's an increasing value of the electron affinity, and as you go from left to right, there's also an increasing magnitude of the negative electron affinity. Well, what exactly do we mean by electron affinity? Well, electron affinity is the energy associated with adding an electron to an element. Now, whereas ionization energy was the energy required to knock one out, electron affinity is the energy associated with gaining an electron. So these are essentially 2 different ways of trying to describe how strongly an atom wants to either hold on to or to gain an electron. So if we look at the idealized reaction, you have an element X in a gas phase. Again, these are defined as being in a gas phase, reacting with an electron to form an anion, X minus 1. And it's the energy associated with this. Again, for most elements, but not all, for most elements, this is a negative value in exothermic reaction. Towards the bottom, I show an element with one of the larger, more exothermic, more negative electron affinities. Fluorine, that element that wants to gain an electron to satisfy the octet rule, to have a filled outer shell, remember, So fluorine will react with electron to form fluoride F-1, satisfying the octet rule. 6 electrons in 2p. And doing so releases 328 kilojoules of energy. When there is a release of energy, we refer to this as an exothermic reaction, and we give it a negative sign. So we say that the electron affinity is minus 328 kilojoules per mole. And then at the bottom I say, as fluorine goes from 1s2, 2s2, 2p5 to fluoride, which has the electron configuration of neon, 1s2, 2s2, 2p6. Now there are a few elements that have a positive or almost zero electron affinity. For example, helium. If you try to have an electron react with helium, to do so would form helium minus 1. That is, if you think about it, helium has 2 electrons in the 1s orbital. It's 1s2. To add another electron, you would have to place it in the 2s orbital by itself. And that's not likely. And so to do this is a positive electron affinity, or it says, yuck, I don't really want you. Helium really doesn't want that extra electron. Metals have a value of electron affinity in the 0 to slightly exothermic, minus 100 kilojoules or so, except for the metals in group 2A, such as magnesium and calcium. And think about that. Why would magnesium not particularly want to gain an electron to form magnesium minus 1? Or why would calcium not want to gain an electron to form calcium minus 1? Well, that's because to add one more electron to magnesium, you'd have to put that extra electron by itself in the 3p orbital. So just as with ionization energy, there are certain patterns in the electron affinity that tell us about the electron configuration of the elements. Another interesting example is the electron affinity of nitrogen. It's about 0, which says that nitrogen, remember nitrogen, 1s2, 2s2, 2p3, 1 electron in each of the 2p orbitals. For nitrogen to add an extra electron to form N-1, you would have to pair up 2 electrons in the 2p orbital. And remember, there is a slight penalty associated with pairing electrons, having 2 electrons occupy the same orbital. And so it turns out that nitrogen doesn't particularly want to gain 1 electron, and therefore it has essentially 0 electron affinity. So basically, ionization energy and electron affinity are measures of a related phenomenon, which is how strongly an atom wants to gain or lose an electron. Electron affinity, gaining, affinity, gaining, affinity for ionization energy, the energy needed to cause it to lose an electron. Now, we talked about the ionic radii of the elements. Let's talk a little bit about what happens to the size of elements or atoms when they become an ion. In general, cations shrink when they lose electrons. Anions swell or grow when they gain electrons. And that actually makes some sense, doesn't it? So let's look at lithium. Lithium, the atom itself, has an atomic radius of about 152 picometers. 1s2, 2s1. That's lithium. If lithium loses an electron, it goes to just 1s2, it has lost the electron in the 2s orbital, and it shrinks because now the orbitals being occupied are at the energy level 1, they're closer to the nucleus. So it shrinks when it loses an electron. Aluminum. 143 picometers is the radius of aluminum, the atom. If you lose 3 electrons from aluminum, it shrinks to less than half of that, 51 picometers. It really shrivels up. Why? Because to lose 3 electrons, aluminum is losing both a single electron in the p orbital and 2 electrons in an s orbital. So it shrinks down, and that's because the only remaining orbitals are the ones that are closer to the nucleus. Anions, on the other hand, when they gain electrons, they swell. For example, if fluorine becomes fluoride. Fluorine has a radius of 72 picometers. if it adds an electron, it swells up, almost doubling in radius when it forms fluoride. So adding an electron causes the atom to swell up as it becomes an anion. Now this graph shows several examples of how cations, which are on the left, the ones that are more gray, get smaller or shrivel up when they lose electrons, whereas elements that become anions, the two rightmost columns, swell up or become larger when they gain electrons to become anions. So you can look at a few examples. Lithium goes from 152 picometers to 76 picometers. It gets small. Sodium, 186 to 102. Now you don't have to know the numbers. Just notice that the significant shriveling or shrinking of the radius when it becomes a cation. Aluminum, 143 to 51. Whereas for the nonmetals, oxygen goes from 73 to 140 picometers when it becomes oxide, O-2. Sulfur, 103 to 184, right? Fluorine, 72 to 133. They don't quite double, but they almost double in atomic radius when they become their most common anion. So in general, when you form a cation, it shrinks. When you form an anion, it grows. Now it's interesting to consider the following series of anions and cations, or species. And the reason it's interesting to consider these is that they're what we call an isoelectronic series, meaning they all have the same electron configuration, 1s2, 2s2, 2p6. They all have 10 electrons. And I'm talking about oxide, O-2, fluoride, F-1, sodium, sodium plus 1, and magnesium cation, magnesium plus 2. And notice the trend in the radius. Oxide is bigger, 140. Fluoride gets smaller, 133. Sodium gets smaller. Magnesium gets smaller. The very bottom shows this again, these trends. Why do we have this shrinkage as we go from oxide, O-2, to magnesium plus 2? In each case, they have the same electron configuration, 1s2, 2s2, 2p6. 10 electrons total. Well, the reason is because there's an increase in the positive charge of the nucleus as you go across this series. That is, in oxide, you have 10 electrons being pulled down by 8 protons. Whereas on the other end of the series, you've got magnesium, 10 electrons being pulled down by 12 protons. So the protons pull those electrons closer to the nucleus. That is, they sort of draw the orbits in closer to the nucleus so that you have a smaller species. Okay, that's the end of this chapter on periodic behavior, periodicity. Next chapter, we will talk about how molecules cooperate and bond together to form molecules via either ionic or covalent bonding. We'll talk to you then. Hope your Saturday night wasn't as bad as sodium's.